A lack of ventilation can trip rectifier breakers for several reasons. Firstly, reduced heat dissipation is a significant factor. Rectifiers generate heat during operation, and if ventilation is inadequate, this heat cannot dissipate effectively. This causes the rectifiers to overheat and subsequently trip their breakers. Secondly, increased battery gassing can be a cause. Without proper ventilation, batteries can experience excessive gassing. As the batteries discharge, they release hydrogen and oxygen. This can create an explosive atmosphere, which can trip the breakers as a safety measure. Thirdly, thermal runaway is another concern. This is a self-perpetuating reaction where a battery's temperature increases rapidly, releasing more heat and causing further temperature increases. Poor ventilation can exacerbate thermal runaway conditions. Considering the provided details, the type of batteries being used, valve-regulated lead acid, is less likely to be affected by thermal runaway compared to other battery types. However, the large number of batteries, 96 in total, each rated at 2.15 volts, backing up a 2400 amp 48 volt DC plant, indicates a substantial amount of stored energy, making safety measures crucial. The described temporary fix, using paper plates as a check valve, is not a permanent solution and could pose a fire hazard. To address this issue, several actions are recommended. Firstly, ensure adequate ventilation. Verify that the ventilation system for the power room is functioning correctly and providing sufficient airflow. This includes checking the exhaust plenum and ensuring that the damper switch is not restricting airflow unnecessarily. Secondly, inspect the rectifiers. Look for any signs of overheating or damage, such as discoloration, bulging, or unusual smells. These signs could indicate a problem with the rectifiers themselves, contributing to the breaker tripping issue. Thirdly, evaluate battery condition. Monitor the battery voltage, temperature, and other relevant parameters to ensure they are within normal operating ranges. Regular monitoring can help identify potential problems early on before they lead to breaker trips. Fourthly, consider thermal monitoring. Install temperature sensors around the batteries to monitor for thermal runaway conditions. These sensors can provide early warnings of temperature increases, allowing for timely intervention. Regarding disabling the breaker shunt trips, this action could potentially resolve the tripping issue, but it should only be considered after a careful evaluation and implementation of appropriate safety measures. It is crucial to understand that disabling breaker shunt trips can compromise the safety of the system. This should only be done by qualified personnel and with appropriate documentation and risk assessment. The shunt trips are designed to protect the system from potentially dangerous conditions, and disabling them without addressing the underlying causes could lead to more severe problems. In summary, the tripping of rectifier breakers due to a lack of ventilation can be attributed to reduced heat dissipation, increased battery gassing, and the potential for thermal runaway. Addressing these issues requires ensuring adequate ventilation, inspecting the rectifiers, evaluating battery condition, considering thermal monitoring, and exercising caution when considering disabling breaker shunt trips. These steps should be taken to maintain a safe and reliable power system. The rectifiers convert alternating current or AC to direct current or DC to charge the batteries, which in turn provide backup power. The rectifiers themselves generate heat as a byproduct of this conversion process. Insufficient ventilation prevents the heat from escaping, leading to elevated temperatures within the rectifier unit. Most rectifiers have built-in over-temperature protection, which will cause them to shut down or trip their breakers when they exceed a certain temperature threshold. A proper ventilation system is crucial for maintaining the rectifiers within their optimal operating temperature range. When batteries are charged and discharged, they produce gases such as hydrogen and oxygen. In a well-ventilated environment, these gases are safely dispersed. However, if ventilation is poor, the gases can accumulate, creating a potentially explosive mixture. The concentration of hydrogen, in particular, needs to be kept below its lower explosive limit or LEL to prevent a fire or explosion hazard. Some power systems are equipped with gas detectors that can trigger breaker trips if the concentration of explosive gases exceeds a safe level. Even valve-regulated lead-acid batteries, which are designed to minimize gassing, can still produce gases under certain conditions, such as overcharging or high temperatures. Thermal runaway is a dangerous phenomenon that can occur in batteries, particularly lithium-ion batteries, but also in lead-acid batteries under certain conditions. It is a process where an increase in temperature leads to a further increase in temperature, creating a positive feedback loop that can result in a fire or explosion. Inadequate ventilation can contribute to thermal runaway by preventing heat from being dissipated from the batteries. Temperature sensors are often used to monitor battery temperatures and trigger alarms or shutdowns if temperatures exceed safe levels. In a power room with a large number of batteries, such as the one described, the risk of thermal runaway is higher due to the potential for heat buildup. The shunt trip is a safety mechanism that causes a breaker to trip or open when it receives a signal from a protective device, such as a temperature sensor or a gas detector. It is designed to quickly disconnect the power supply to prevent damage or injury. Disabling the shunt trips can eliminate the nuisance tripping issue, but it also removes a critical layer of protection. Before disabling shunt trips, it is essential to identify the underlying cause of the tripping and implement corrective measures to address the problem. This may involve improving ventilation, replacing faulty rectifiers, or adjusting battery charging parameters. It is also important to consider the potential consequences of disabling the shunt trips, such as the risk of fire or explosion, and to implement additional safety measures to mitigate these risks. A qualified electrician or power systems engineer should be consulted before making any changes to the breaker shunt trips. Implementing a robust monitoring system that tracks temperature, voltage, current, and gas concentration can provide valuable insights into the health and performance of the power system. This data can be used to identify potential problems early on and to prevent breaker trips. Regular inspections and maintenance are also essential for ensuring the reliable operation of the power system. This includes checking the ventilation system, cleaning the rectifiers, and testing the batteries. By taking a proactive approach to maintenance, you can minimize the risk of unexpected downtime and extend the life of your equipment. The ventilation system plays a critical role in maintaining the proper operating environment for the rectifiers and batteries. A well-designed ventilation system should provide adequate airflow to remove heat and prevent the accumulation of explosive gases. The ventilation system should also be equipped with filters to remove dust and other contaminants that can impair the performance of the equipment. Regular maintenance of the ventilation system is essential for ensuring its continued effectiveness. This includes cleaning the filters, inspecting the fans, and checking the dampers. If the ventilation system is not functioning properly, it should be repaired or replaced as soon as possible. When evaluating the battery condition, it is important to consider several factors, including the battery voltage, temperature, and state of charge or SOC. The battery voltage should be within the manufacturer's specified range. The battery temperature should be monitored to ensure that it does not exceed the recommended operating temperature. The state of charge indicates the amount of energy stored in the battery. A low state of charge can indicate that the battery is not being charged properly or that it is nearing the end of its useful life. There are several different types of temperature sensors that can be used to monitor battery temperatures, including thermocouples, resistance temperature detectors or RTD, and thermistors. The choice of sensor will depend on the accuracy and temperature range required. The sensors should be placed in close proximity to the batteries to ensure accurate temperature readings. The data from the temperature sensors should be logged and monitored to identify any trends or anomalies. If the temperature exceeds a safe level, an alarm should be triggered to alert personnel. Before disabling any breaker shunt trips, it is essential to perform a thorough risk assessment. This assessment should identify the potential hazards associated with disabling the shunt trips and the measures that can be taken to mitigate these risks. The risk assessment should be documented and reviewed by qualified personnel. The decision to disable breaker shunt trips should be based on a careful consideration of the risks and benefits. If the risks outweigh the benefits, the shunt trip should not be disabled. If the shunt trips are disabled, additional safety measures should be implemented to protect the system from potential hazards. These measures may include installing additional temperature sensors, improving ventilation, and implementing a fire suppression system. It is important to note that disabling brake or shunt trips is a complex issue that should only be addressed by qualified personnel. A thorough understanding of the power system and the potential hazards is essential for making informed decisions. The rectifiers convert alternating current or AC power from the utility grid into direct current or DC power. This DC power is then used to charge the batteries and to power the DC loads in the data center. The rectifiers are typically located in the power room along with the batteries and other power distribution equipment. The rectifiers are designed to provide a stable and reliable DC power supply, even when the AC power from the utility grid is interrupted. The batteries provide backup power in the event of an AC power outage. The batteries are sized to provide enough power to keep the DC loads running for a certain period of time, typically 15 minutes to several hours. The batteries are typically lead-acid batteries, but other types of batteries, such as lithium-ion batteries, may also be used. The power room is a critical part of the data center infrastructure. It is essential to maintain a safe and reliable power supply to ensure the continuous operation of the data center. The power room should be designed and maintained in accordance with applicable codes and standards. The power room should be kept clean and free of clutter. The power room should be properly ventilated to prevent the buildup of heat and explosive gases. The power room should be equipped with fire detection and suppression systems. The power room should be accessible only to authorized personnel. In addition to the above considerations, it is also important to consider the impact of humidity on the power system. High humidity can lead to corrosion and other problems. The power room should be kept at a relatively low humidity level. The use of paper plates as a check valve is not a permanent solution and could pose a fire hazard. A proper check valve should be installed to prevent backflow of air. The check valve should be sized to handle the airflow requirements of the ventilation system. The check valve should be made of a non-combustible material. The location of Tampa, Florida is a warm and humid climate. This can exacerbate the problems associated with heat and humidity in the power room. It is essential to take extra precautions to ensure that the power room is properly ventilated and cooled. The 48-volt DC plant is a common voltage for data center power systems. The 48-volt DC plant is used to power a variety of equipment, including servers, network devices, and storage systems. The 2400 amp capacity of the DC plant is a significant amount of power. This indicates that the data center is a relatively large facility. The 96 2.15-volt VLRA batteries are connected in series to provide the 48-volt DC power. The batteries are arranged in multiple strings to provide the 2400 amp capacity. In summary, the tripping of rectifier breakers due to a lack of ventilation can be attributed to reduced heat dissipation, increased battery gassing, and the potential for thermal runaway. Addressing these issues requires ensuring adequate ventilation, inspecting the rectifiers, evaluating battery condition, considering thermal monitoring, and exercising caution when considering disabling breaker shunt trips. These steps should be taken to maintain a safe and reliable power system. Consider consulting with an expert to determine the best course of action for your specific situation. The expert can assess the power system, identify the underlying causes of the breaker trips, and recommend appropriate solutions. They can also help to ensure that the power system is operating safely and reliably. Remember that safety is paramount when working with electrical systems. Always follow proper safety procedures and consult with qualified personnel before making any changes to the system.